Hey everyone, I'm Tom McQuillan. I'm here with Natan Biesmans, and we're going to go through VIMs. Natan, why is this presentation important?
So this presentation came to be due to the work I did with G²CPU. When I started developing the toolkits, I soon realized the only way forward with all the functionality that I needed was to use Malleable VIs. I've been using it quite intensely for a couple of years already now. And I learned so many lessons that I just couldn't find online. And I thought, I have to share this. So that's this presentation. And I thought my good friend Tom, you might enjoy joining me here. So I invited him, and here he is.
Yeah. Unfortunately, Tom couldn't show up, so I'm here instead. Did you add animations to this? Okay, good.
Couldn't resist.
All right.
Cool, let's start.
Nice one. So I'll kick things off. And actually, I'm just going to share my screen to start with, because I'm not very good at following PowerPoint slides. But anyway, this first slide, why should we use VIMs? I guess that should really be called, when should we use VIMs? Because they're not suitable for absolutely everything. However, I do use them on a daily basis, and I use them for a different reason than Natan. I use them to make my own life easier, and as we'll see later on, Natan uses them to make everyone else's lives easier with his new toolkit. I'm going to be doing all of these presentations in LabVIEW 2024. So if Zoom irks you off, I'm really sorry, but it's what I'll be using. I thought we would take a trip back to 2019 before we had VIMs, and instead we had polymorphic VIs. So we've got an API here that I'm sure we're all familiar with. It's the INI configuration file API, where I can write a section and key value to a file, and this will accept different data types: a string, Boolean, and numeric. Now that's all very well and good, but if I try and wire something else, let's say I want to create a, just write a cluster to this INI file. All of these elements have names, they all have data, so I should be able to wire that up, but I can't. So now let's have a look at what it would take to expand this functionality. Well, okay, what is this function? Well, actually, it's a polymorphic VI. It's just had its icon hidden, and it will only accept these data types. If I right-click and open up the polymorphic VI itself, you can see that to add support for new data types, I would need to create a brand new VI, add it to this list, and then it will work. But again, I need to create a new VI for every single data type, which sort of sucks. So OpenG came along and tried to solve this issue using variants. And this is a function I use from their variant configuration library, where you can have a cluster and you can write it to your INI file, and it will parse all of the names and all of the data and throw it into your file. That's great. But we have a coercion dot. I'm not too concerned about that. That's fine. The issue then comes, okay, reading data. If I scroll along here, reading data from the native API, we're still restricted by these data types. The data types you see here, we can't define new data types. But again, OpenG came along and solved that issue for us, where we can define the type of data we want to read, and it comes out as a variant, which again isn't amazingly helpful. You can't unbundle this variant and see the data inside. And so whenever we use this get data function, we must use the variant to data function alongside to get some useful data. Which, as a developer, isn't great. Like, whenever I see variant data, I wish there was an alternative way. And it would be nice if we could just wrap all of this into a single function, because they always need to be used together. So if we select both of them, we can create a VI from selection. I'll just highlight all of that, right click, VI from, what am I doing wrong, Nathan?
What do you mean? What are you doing?
I was trying to create a VI from selection. I thought I was right click.
Create sub VI.
Okay, yeah. Edit, create sub VI. Save. Yes. And click OK. So now I have a sub VI that will encapsulate both. But it's not going to propagate the data. You can see that the data in doesn't match the data out. And it won't do that unless I create this as a malleable VI. And this is where we start seeing the power of VIMs. So if I open up this function, file, save as, rename, continue, and I can save this as a Vim just by changing the file extension. So untitled 11 subvi dot vim, click OK. And now you can see that immediately something has happened to the data types. LabVIEW has recognized that this function wants to do something with these data types because it's, well, broken them all. And in this presentation, we're going to explore how we can configure all of these data types. So I am going to just delete these as we go through some other bits of code. On the screen here, we have a very similar concept to before, where we wanted to propagate data into a function. This is a Vim I use quite frequently, where I have some sort of collective data type, whether it's a set, a map, an array of some dimension, or even a cluster, and I want to know the size of it. Perhaps I'm receiving this data over a network, it's being formatted into a dynamic data type, and I just need to know how big it is. Well, these are all the same function. And if I open up this function, we can start to see how that data type is being asserted.
Maybe also a great thing to note here with the 2D array size, you immediately get the feedback as a developer what you can expect when you put a certain data type in it.
Yeah, absolutely. That's a great point. We'll come on to that in one of these frames. So actually, just on the chat, how many of you use Vims? How many of you have seen this type of structure before? I don't know how much of a delay there are.
Yeah, quite a lot of people have used it.
Quite a few.
Oh.
Quite a few, not. Okay, mixed. Fine. Okay, so. Okay, but there are bugs on broken wires. Yeah, we'll come on to those. Okay. So one of the fundamentals about Vims is type assertion. And the way we can deal with that is using the type specialization structure. A structure you will find alongside your for loops, while loops, time structures, etc. down here. This is a very special type of structure because it's always evaluated during edit time, i.e. when you're developing code. And the way that this structure decides, which case it's going to execute, I'm not used to this shortcut yet, Control Shift scroll wheel, will be, it starts on case 0 and it sees if it can compile them. If not, then it will move on to the next case. If it can compile that, then it stops. If it can't compile, it will move on to the next case. Case number 2 here. Now, when you're developing these cases, we need to pretend like each of these inputs is changing. So in this vim, I have a set. And so with a set, I can use the collection size function. And that will return a size. This will work with a map as well. If I move on to the next one, when I programmed this case, I used the array size function. And sort of in my developer mind, I had to pretend like, instead of a set being here on the front panel, this was an array on the front panel. And as Natan pointed out earlier, like the output of this function could be a 1D array, one element for every dimension of this array.
By the way, you could verify the behavior here by just adding a couple of constants in there to just quickly wire it through your case structure or your instruction structure to verify the behavior.
That's a great tip, and I'll show you that on the next piece of VI. And then finally, I was feeling a bit fancy, and I was like, could I use the same vim to evaluate clusters? How many elements are in my cluster? And so this is a way that I implemented it. I'm going to think, okay, I have a cluster in here, and in my demonstration down here, this is an error cluster. And I'm going to see, is LabVIEW able to unbundle this cluster using an unbundle function? If yes, it means it is a cluster. And so this case will be able to compile. But because it's a set here, we get a broken wire and it can't compile. Let's head over to this VI, which shows it a bit more clearly. And one that Natan just reminded me exists. So in this example, we have an error, we have a float, we have a string. And we have 3 cases, one for each. See that starting with case 0, this one's accepted. So we're not going to bother looking at 1 or 2. But if I change the input data, you can see that case 0 is now declined. Case 1 is declined. Case 2 is now accepted.
And what is that assertion VI that you're using?
This one.
The previous
one. Assert floating point numeric.
Yeah.
And so these functions you see in here are all part of the assert type, which you can find in your comparison palette. So right-click, comparison, assert type. It's in the comparison palette because we are comparing data types. If this is a function I will use more often than not, assert structural type match. With this function, you can basically define your own custom data types that you want to match. You're not reliant on whether it's a float or an integer or a string or an error cluster. You can define your own data types or define data types you actually do not want to match.
Maybe also a quick tip here, the other assertion functions, they're actually also VIMs. So you can actually open them and see how they are configured internally. If you want to do something similar, but not quite as much, you can use it as a basis for your own development.
Absolutely. So there's a question in the chat from VJ. I never did figure out where the assert array dimension count and assert dimension size differ. Let's have a look at both of those. Your question is assert array dimension sizes and assert array dimension count. Natan, do you know the answer to this?
I'm going to be quite honest with you. It's something that's eluded me also for quite a while. I knew it for a bit, and then it just got lost.
Oh, does one of them give how many elements are in each dimension, and the other just tells you how many dimensions there are? I think
Yeah,
that's what the Medlin's saying in the chat.
Yeah, the problem is during development time, you don't always know how many elements are in your array.
Oh, Jesus. Interesting. I have looked at these VIs before, and okay. Okay, VJ saying they broken. I'm quite curious, so we can talk offline about this. So we're going to have a look at a couple more of these VIs later on in the presentation, including how we can dynamically create maps from different types of cluster, like you see here. And Natan, shall we pop back over to the slides?
Yeah, there we go.
Nice one.
Mind popping out? Did he just leave? There he is. Okay, so let's quick recap. Tom, are you muted or?
I was muted. Yeah.
Okay.
Hang on. One more thing, I promise. Okay. So we're also used to data types changing just like randomly in LabVIEW as it is. All of your mass functions can accept different numeric representations, including different scalar sizes. So if it's an individual scalar or an array or n-dimensional array.
Or even
if we look
clusters.
At this example, oh yeah, I always forget about that one where you can add clusters together and stuff. So data in here, this is a U32. I can change that to be a float, a double here, and you can see it changes color. You get that visual feedback Natan was talking about earlier. If we change the array size, you can see everything is still very happy. And we can have n dimensions like so. Now, it would be nice if we could wrap this inside a VI. And so that's what I've done here. So this is a simple VI function dot VI, a static VI that we have in LabVIEW. And you see we have a coercion dot here, which means it is going to coerce from a double into an integer, is what it expects. If I change this to multi-dimension, it's just going to break. However, by simply changing the extension here, making it into a malleable VI, and changing some of the execution settings, which we'll mention earlier, we can make it so we get true type propagation, like we see with the primitives, where as we add more dimensions, I'll delete that one. As we add more dimensions, they're propagated through as we change the data type, the representation, at least. You can see that that type propagate. Okay, now I'm done. Very sorry.
All right. Okay, let me just quickly pop back into the presentation so we can do a quick recap. Tom, you do the honors.
Cool. So we have special VIs called malleable VIs or VIMs, techniques or dynamic code execution, basically referring back to that type specialization structure I pointed out earlier, where LabVIEW will decide which frame is going to execute, but specifically during development time. So
yeah. You can go quite far with this. So within this structure, you can put separate VIs which can do a lot of function calls. You can even nest malleable VIs within malleable VIs to get a layered structure. So you can create your malleable VIs in such a way that they're drastically reusable.
Yeah, I've gone quite, yeah, many layers of VIMs, for better or for worse. All right, next slide.
Okay.
We looked at type specialization structures and how they can adapt to different types, and how LabVIEW decides which frame is going to execute.
Maybe a cool thing for those of you that have used G²CPU, the code you're currently seeing on the screen is the exact code which allows the functions to accept both GPU objects, so data you have on your GPU, as well as LabVIEW scalars and LabVIEW arrays. So if it sees that you put in a LabVIEW array, it will automatically know, hey, I need to upload this to the GPU before doing the rest of my operations. So this is the simple concept that makes it work.
Nice one. It's just a comment in the chat from Ed. Do VIMs work with inline processing? Yeah, they need to be marked as inline. That's one of the execution settings I was referring to earlier.
Okay, next slide.
Yeah, next.
Assertions.
Assertions. We also looked at this. We can make it so VIMs are as general or as concise as you want, whether you want them to work with specific type defs or with basically all data types.
Maybe also a cool thing here about the code that you're currently seeing. This is also from G²CPU. And this is where the translation happens between what a scalar object, or a LabVIEW array object is, and the corresponding G²CPU object. So this is the only location, or the only VIM, that actually defines what data type corresponds to which GPU object. And I can reuse this Malleable VI as many times as I want, and it nicely holds all that data. A cool thing here is you can see here a double layer of structures. And the idea here is I first have an assertion, and if this one breaks, it won't try to go through all the other test cases. It will automatically go to the next one. I did notice some performance improvement in the development environment by trying this technique.
Nice one.
Okay.
Next.
When should we use them? So Malleable VIs, they do have a really specific use case, or a set of specific use cases. So it's not like you can just pick them up and they will fit every purpose. So the first thing we need to ask is, where is our code being evaluated? Where is our decision being evaluated? Is it during runtime, or is it during development time? During runtime, it means our code can dynamically change its behavior. While with development time, it changes its behavior when we're developing, so the developer knows, hey, I can now do this, or I can now do that, immediately getting that feedback. And think of the polymorphic VI Tom showed, or just the Malleable VIs that developers can see what's happening. Case structures is a nice example of runtime evaluation. They do have the caveat that often you don't really have a lot of cases, and they're normally fixed. You just have each case containing your code, and that's it. Also, the permutation count tends to be small. There aren't many cases where it's applicable that you should have 100 cases. It just slows down your VIs, and then maybe it's better to go nested or something like that. Next up, LabVIEW classes. It's another way of dynamically changing the behavior of our codes. These are quite interesting. We can load them in during runtime, so we can have a lot of permutations going on. It's quite flexible. When we designed our code, or sorry, we might be using classes or children that didn't even exist when we designed our code, and it will dynamically accept them as we go. Then we have polymorphic VIs, like Tom showed, where we have our VI, or we create a separate VI for each case. and assign them to an overarching parent VI or polymorphic VI. Again, the permutation count tends to be quite small. You can only have as many cases as you have VIs. And also, again, it's fixed. You can't add behavior quite quickly. You need to manually start adding them like you intended, like Tom beautifully has shown. And then lastly, we have malleable VIs. I think by now you're seeing the pattern. So here, well, it's really flexible. We can design malleable VIs only to realize later that it also works on another data type, like, for example, doing addition with clusters that you didn't think of, but because you designed or you just placed it in there, your code will just accept it because LabVIEW accepts it.
One thing I found, though, that's just as much a curse as it is a blessing. I've created a couple of VIMs in Venn as a developer who's forgotten how that API is meant to use, seeing, it accepts this data type, which it wasn't designed for in Venn. It's given me, let's say, unexpected results.
Yeah. So yeah, that's definitely something to watch out for. And when I was developing, it was sometimes I made a mistake where I had a Boolean, but it actually accepted an error wire because they were linked to a case structure and that kind of thing. So it's definitely something to watch out for.
Yeah. Also, VJ saying, the one main difference between VIMs and polys is with polymorphic VIs, you can change your connector pane. That's
true.
Like also, if you think of DACMX, for example, DACMX create, like the thermocouple input function is horrible, where you have inputs coming from all sides.
Not only that, with polymorphic VIs, you also have the nice drop-down menu. So I am a little bit sad that that's not applicable, or that polymorphic VIs don't accept malleable VIs, that you can have that drop-down menu that you can change behavior.
Yeah.
Okay. All right, let's get on to the next one. So advanced techniques. So here we're going to have a look at a couple of techniques I've used within G²CPU, where I start looking at, okay, how can I make my API scalable for other developers using it, rather than, okay, how can I make something for me or for my customer? So the first thing the first thing I want to talk about is LabVIEW clauses. They can actually be really useful with malleable VIs. We can actually use them with the parent-child structures to actually assign attributes. So we can, for example, say, hey, I have here a car wheel and a cart wheel, and both have the attribute wheel, which is their parent. So when we say, hey, I have a malleable VI that should accept only wheels, we can just say, okay, only accept wheel classes and don't accept anything else. So we can use that to allow for IDE decision making. Let's say, for example, with G²CPU, if some functions only support integers or only support floating points, that we say please only use floating points. And please break the block diagram if an integer has been provided. Another neat thing is when using LabVIEW classes, with malleable VIs, we can actually use the children, or we put out the children rather than the most common parent, which means we can have different wire colors, which again gives developers a lot of feedback when they're developing. And probes. Each child can have its own probe, which then is being called when it's assigned to the wire. So you can write your code, you can immediately put a probe down, and it gives you the information you need instead of trying to create some kind of generic probe in the parent. And I've also found that they tend to have a lot more, when you have malleable VIs and classes, they have a lot more flexibility than dynamic dispatch. You can have dynamic dispatch code within the malleable VI, but you can have multiple inputs and on your malleable VI and make decisions based on the data types provided in. a good example of that is, for example, the addition. When you provide an integer and a floating point, the output should be floating point, no matter what side they were put into the addition. So for this, I've made a quick example. So here we have our car, and we see here nicely, okay, we have a couple of colors. So we have a function here saying attach, and we're going to try and attach a car wheel, a cartwheel, and a toy wheel, and see what happens. So currently, the colors really pop out. People using your API, they can clearly see what the data is. And my screen just dropped. I think it's back. Okay, cool. So here you can see I'm putting down a probe. I have a car. Unfortunately, my car doesn't have a wheel, so I'm going to attach a wheel to it. So here I'm attaching a car wheel, and immediately the probe says, hey, well, you attached it, so there's a car with wheels. Now, let's see what happens if we add a cart wheel. Those wooden wheels, you can clearly see the colors changed. Developers can immediately see what's going on, and when we put down the probe, the assigned probe also changed. But what if we add a wheel which we didn't allow? In this case, within this VI was assigned explicitly, but if a toy wheel is attached, no, you can't attach toy wheels to your car. So let's break the codes. Your developer provided some data for which your VI wasn't designed, or which just doesn't make sense. So let's break the block diagram. Let's break the code and say you couldn't do this, which is great. If you have this during development time, your developer knows immediately something is wrong, rather than, hey, I'm developing this, my code compiles, so let me run it. And then suddenly during testing, he knows, hey, there are these errors for which I need to account. So it drastically reduces the loop time of developing and testing.
One thing I've also found is it also reduces the developer time. Because before I got really into Vims, I would create lots of what we call like boilerplate class code, where you create these layers of classes which you know aren't going to be used, but you create them, and so you have abstraction layer for your data, and you can make different things work, different objects work with other objects, which will work, but it's very complicated, and as Natan said, you don't get that developer time feedback. Whereas using Vims, you can strip away a layer of abstraction and still get immediate developer time feedback as to whether it's going to work or not.
Exactly. So next up, let's discuss. Did you just?
Yep.
Let's pull me out of my flow. So let's discuss interfaces. So I said, with classes, the parent can define an attribute saying, hey, when I have the attach function, accept car wheels, but don't accept accept wheels, but don't accept doors, because you can't attach a door to your wheel socket. But what if we have more attributes on which we want to filter the behavior of our Malleable VI? Well, we can just use interface classes to do that for us. We can define interfaces saying, well, my cartwheel is made of wood, my car wheel is made of metal, my toy wheel is made of plastic, and all are a child of the material class. So we can even add more fidelity to, okay, this is allowed and this isn't allowed. Also, we have more wires that we can control, that we can put out if we want. We have more control over probes. And if we look here at the example, so here I have a probe, my cartwheel, and if I burn my cartwheel, I get charcoal. Wooden cartwheel burns, great. If I try to burn my toy wheel, which has the attribute plastic, or a plastic interface attached to it, you can see the wires already changed to black and green, and you can see suddenly I get molten plastic. And then within this example, car wheels are made of metal. So if I try to do that, it's just going to say, yeah, I'm not accepting the metal interface. So break the code. this is now one input. You can do this with a lot of inputs. Multiple, compare them to each other. You can go quite far in these types of comparisons. Okay. Left view core functions. Tommy, you're on. Oh,
cool.
PJ,
So,
I have a question. This was interfaces. Yeah, so this behavior was just defined by interface. So the interfaces themselves don't implement any methods per se, but we use them as a mechanism to filter the behavior to say these functions are allowed, and these data types are allowed, and these other ones aren't, and even change the behavior of the outputs. So the output data type based on the interface being used. Okay, second try.
cool. So looking at LabVIEW core functions, now I showed you some of this previously directly in LabVIEW, and when using VIMs, we do have a bunch of assert functions where you can compare data types, but actually the easiest way I found of using VIMs is using core primitives. This is an example of a SecGem API I was developing. This isn't the actual application code, just a quick mock-up I created for this presentation. But effectively, I had to send messages, user events, with a payload which was varying a cluster size. I knew that cluster was always going to have string elements, but I didn't know how many elements were going to be in these clusters. And for various API reasons downstream, it had to be a string cluster, just the varying sizes. So I wanted a Vim that could accept that. And so on the left-hand side, you can see this API in practice, where it would only accept homogeneous clusters, strings. So this one won't work. On the right-hand side, you can see I'm just using the variant to, sorry, not the variant to string, the cluster to array function as a LabVIEW primitive. Now that function is going to break if you try and wire in a homogeneous cluster. But a cluster containing, heterogeneous, yes. Yeah. So a cluster containing different element types. The other thing, as if that wasn't a safety net enough, I'm also strictly typing my data type going into this generate user event by defining the names and values as string arrays. Yeah, next one.
So this is quite cool because your library nicely scales without creating an instance for each permutation. Awesome.
Like with polymorphic VIs, each of these would have to be a separate VI instance, a separate VI that you put in.
Or some awesome variants code. Okay,
I don't like dealing with variants. I teased you with this VI earlier, where it's just that how big is a thing.vim, where you can wire in collections, arrays, and even clusters. Again, here I'm just using core primitive functions. So for sets and maps, I can use the collection size. For arrays of n dimension, I can use arrays, so array size. Then for clusters, again, I'm using a LabVIEW primitive, which is unbundle. So any cluster in LabVIEW can be unbundled. I'm then using some, if you're curious, some OpenG functions to have a look inside this cluster. I think there's two more. Oh yeah, this is a.
Sorry, did I miss something?
Huh? No, go on. This is a technique I use all the time, and I was really pleased when I sort of discovered it. This is a function which can change between arrays and sets. And so on the right-hand side, where we have this array going in, at some point you need to define what the data type of this set is going to be. So using a diagram disable structure, in the disable case, I suppose that would have been a better one to show in this image. Nathan, if you go to the next slide, maybe there's, yeah, okay. So in the disabled case, you can see that this is where I am building that data type. However, that data type is never going, however, this code, sorry, is never going to execute because it's in the disabled case. However, that tunnel, if you go back a slide, Nathan, that tunnel is marked as use default value if unwired. So the default value of that data type will be used to initialize my shift register. Then I can use my insert into set function.
And that's why you're feeding this in, so you can make the composite. All right.
A very similar story for maps. I wanted to be able to pass in a cluster. Again, this was for another project where strictly typed clusters had to be used previous in the code. But like before, I'm using a diagram disable structure to define the default value of my map. And this bottom one is a homogeneous map where it's like string name, string value. But the top one, I'm using a variant because the cluster input is made up of multiple different types. In this case, a cluster with a string, a Boolean, and a numeric.
Okay. All right. Next up, we have mathematics. We can actually do we can add a little bit more intelligence in our functions. So here we have a function from G²CPU where we can index an array. So we can put a 1D, 2D, 3D, whatever in, and we can index for a certain amount of dimensions. And during development time, it will automatically realize, oh, okay, I'm using this data type, which is this dimension. I can subtract the amount of indexes added, and the output will be this specific dimension. So if we just quickly visualize this, so here we can see, oh, okay, I'm indexing a 4D array with one index. It accidentally got clipped, but I'm adjusting the data type here. So you can see it nicely propagates through, like we've already seen with Malleable VIs. But we can also add a little bit more intelligence here. So you can see here the wire is broken now that we have two indexes. And so if we decrease the dimension, it suddenly works again. If we decrease the input dimension, we can see, hey, suddenly the wire is broken again on the output. And so, well, we need to adjust the dimension once again. So we can define this type of functions or this type of intelligence in there, and actually, give the developer all the knowledge he needs, rather than having an instance for each polymorph for each set of indexes you want to do, or mandating that you need to do a cascade of indexes or stuff like that. So the way that this was implemented, well, is by, sorry, lost my train of thought here. So the way this was implemented was using dimension counts. So first of all, when using mathematics in the IDE, it's definitely not Turing complete. You're not going to be able to do everything that you want to do, but it will definitely get you a long way. So we can use LabVIEW functions to, for example, increment or decrement. So if we want to go from one dimension or a count to 2 dimensions, well, we can just use build array. If we want decrement, we can use index array. So let me see here. Yeah, so we can combine this for functions. So if we want to subtract dimensions, if we're searching for the biggest dimension between 2, we can use these increment and decrement and the structures to define, oh, okay, this is what's supposed to happen, what's not supposed to happen. So the subtract dimension code you see here is actually the logic that's being used by that VI to say, hey, I have a dimension count here, I have a dimension count there, subtract them from each other or keep decrementing them until they are the same. and then put out subtracted array. Quite simple, but it does require a different way of thinking than from normal LabVIEW. Now, next up, we can also use clusters. So as you've seen, I was doing more than counting in that video. I was adding values to that cluster, and based on the amount of values in there, calculations were done, or the counting was done. So this is actually the code in there. So we have data coming in, or our indexes coming in, and I'm just causing them from a cluster to Vijay is saying the previous example only works for a limited amount of dimensions. Yes. So it only works. Why wouldn't it work? I'm not familiar with the limits to dimension counts within LabVIEW, but normally there shouldn't be a limit. I mean, yeah. If you put in a 10-dimensional array. Oh, like that. Yeah. This is not recursive. So you will need to add more layers on this if needed. In my case, G²CPU and the underlying engine only goes up to 4 dimensions. It's just the way how GPU memory sometimes is structured. And that's why I could limit it to this. So again, I can't stress this enough. It's not Turing complete. You can't do everything you want to do with it, but you definitely can go far. Okay, clusters. So cluster to array, so to index all the values. Whoops, sorry about that. So we can use that to index, and I use that internally to then go through each index and execute a sequencer. We can add dynamically more to them, and they can be evaluated, both their values and the amount of data in there, which is something you can't really do effectively or intuitively with arrays. And of course, like I said, we can convert them to arrays, either to an array of numbers, or if you have nested clusters, it just becomes an array of clusters, which is also part of the index function, but not really part of the video. Next up, debugging.
Yeah,
Tom,
I'll take this.
What's your opinion on this?
Debugging VIMs. Debugging VIMs can be quite challenging. We've already specified that VIMs are inlined, which tends to strip out all of the debugging tools, the debugging features we have in LabVIEW. And so with VIMs, I always unit test my VIMs in the testing known cases, so I can be sure that the function actually works. Failing that, what we see on the screen here is converting that VIM into a standard VI. And I think this is the right-click menu I got confused with earlier, where we can just freeze the state of that VIM using the types which are defined on the block diagram into a standard VI. And then you can change your execution settings, enable debugging, etc.
Yeah, so this actually works great because your Malleable VI is more than defining the IDE behavior, of course. You're going to put in code in there, and sometimes your code is not going to do what you expect it to. And then this is absolutely a great way to quickly verify what's happening underneath, because, well, you can't open a Vim and put in execution highlighting or probes. It needs to do like that. Yeah, so when you change this, you need to enable debugging. It's not enabled by default, which I'm a little bit of pity. Also, if you make changes in that VI that's converted, there's not an easy way to go back. So you need to copy over your changes back to the Malleable VI.
Although once you've found the issue, update your unit tests. So your unit test captures them, and then you're forced to update your Vim.
Ain't nobody got time for that.
Everybody got time for that.
Well, talking about unit tests, so with Malleable VIs and G²CPU, I got a little bit of an issue. So my functions, like simple addition, it supports 4 dimensions, 13 data types on the GPU side, but then also the same values on the LabVIEW side. And I support scalar values, which, if you have an addition, actually comes down to almost 14,000 permutations, which, yeah, creating a test hardness for each permutation, I didn't really feel like that, especially because there are hundreds of functions and even some have more inputs. So I actually created a toolkit to make unit tests with Malleable VIs and actually do the assertion automatically. So you can define your behavior and actually see what the output is, compare it in a more dynamic way than creating a test harness for each case. So for anyone that wants to use it, I made it fast, free and open source. You can just download it on my GitHub, free to use. It's still under development, but it's definitely already ready to use. I just need to remove some of the rougher edges. But the great thing here is, so all we're doing is we're calling this VI. In this case, in this example, this is within Karaya, where we're defining a variable that we're setting. So that's actually the mechanism with which we change the internal behavior. And all we have to do here is a conditional disable diagram where we define the behavior, define, okay, this is the test cases we want to do. So the neat thing here is we can just stack the cases depending on what we want to do and feed them in. Now, in this case, there's only one input, but it was specifically designed to allow for parallel cases, nested cases, so you can truly work with test vectors saying, test each case in this for each case in another one. So if you have 10 cases in here and you have 10 cases in another one, suddenly you're doing 100 permutations. So suddenly it becomes a lot easier to test those 14,000 cases of an addition. So this is a great way to verify behavior, both intended and unintended, in an automated way. So like I said, cycles through states. And the benefit here, like I said, is a single test harness instead of creating 14,000 for a single Vim. And we can use for the structures for vectors. I verified it with Karaya or JKI, and I also tested it and verified it with the NI unit test framework. So it just works. You place in the VI, you configure it, and it will run it, and then based on that, you can actually see the output. So this saves a lot of time, or at least it saved me. Okay. So the assertion VIs are Vims. Some of them are. So some of the assertion VIs are Vims. And as far as I'm aware, there are only two primitive assertion VIs. So either assert structural match or assert structural mismatch. All right. So wrapping up, we're getting to the end of the hour. So let's talk about features of Vims. So yeah.
Do you want to go first?
Yeah, sorry. So we can't expose Malleable VIs directly in PPLs. And this is just purely because, well, PPLs are compiled, while Malleable VIs, by their very nature, are uncompiled, where their behavior is defined during the compile time.
Yep. Next one is, we've mentioned this a few times, but because Vims are inlined, the call chain doesn't know that it's in a Vim. And so if you have any special error handling, your source is going to appear as your calling VI, which sometimes is helpful, other times less so.
Another thing to keep in mind is memory usage. Whenever you use Malleable VI, a copy of that Malleable VI is placed within the file of the calling VI, which, if you have a cascade of functions, can become quite big. And this is something I've been battling with G²CPU, where if you have a Malleable VI, which is called by another Malleable VI, which is called by another Malleable VI, each level creates a copy and stores it in there. So it becomes an exponential problem. So it's definitely to look out for. And if possible, try to keep the amount of not recursion, but levels of Malleable VI calls to a minimum, because you will notice development time slowdowns, because the IDE tries to load in the entire VI and also the copies within that VI, but then also tries to load in the Malleable VI. So there's something still not completely right, in my opinion, there, but I hope NI is going to work on it.
Speaking of things that aren't completely right, occasionally the LabVIEW IDE will gaslight you into thinking your code's broken when it's not. I've seen various instances where you've got your Vim on the block diagram and you have broken wires going everywhere, but your run arrow is perfectly fine. You can click the run arrow, run the code, it's fine. Even when you close your VI, reopen your VI, you still have those broken wires, but everything appears fine. To get around that issue, I found either, so long as it's just that one VI, you have in memory, either recompiling it or opening up your Vim and changing the connector pane, and then changing it back, like setting an input to required instead of optional, for example.
Maybe also an addition on that one, and I actually think it's linked to the previous previous item I discussed. Especially in older versions of LabVIEW, it was possible that you put in valid types in Malleable VI, and still you would get a broken runtime arrow. And then just closing the VI or doing a mass recompile, or sorry, closing the VI, opening it again, or doing a mass recompile suddenly fixed the issue. So it was one of those little quirks. I haven't really noticed it on LabVIEW 2024, but I do notice it when I'm using LabVIEW 2020.
Yeah.
Yeah. And then maybe also probes. So an interesting thing is, well, if we place down a probe, which is using a specific class, what happens with that probe if we change that class by changing the input? Well, it doesn't. LabVIEW is not that smart, so you're going to get some weird behavior where the probe is there, but technically it's on the wrong class. That being said, I haven't noticed it. Haven't noticed it really hampering. It's just close the probe, open it back again.
Okay. Question from the chat window. You said that Vims and PPLs don't work well together. What about Vims and NI packages or executables? The reason why Vims and PPLs don't work well is you can have a Vim in a PPL. That's fine, so long as that Vim is private. You can't expose that Vim.
So your functions
a public function.
So your functions within the PPL can use as many Vims as they want. They can use G²CPU. I verified G²CPU within PPLs. That's absolutely not an issue. But once it's in a PPL, it can't go out. Only the VIs you created, which are calling the Vims, can actually use it.
Yeah, I mean, Casey suggests not putting Vims in PPLs at all. I've seen fruity LabVIEW behavior with Vims and PPLs, but ultimately they are LabVIEW bugs which will be fixed. And so Vims and PPLs should be fine.
Hamed is asking, is it possible to use LabVIEW class methods as malleable VIs? So what I tend to do is actually, so a lot of G²CPU is actually just calling class methods. But I'm just encapsulating that with Malleable VI to handle all the extras around it for that development time behavior.
And what? Sorry.
Oh, yeah. Go ahead.
Well, I was just thinking, whenever I create a class just to strictly define a data type, it's at that moment where I think, oh, could I start now using Vims instead of creating a few layers of class hierarchy?
And sometimes a hybrid solution is
absolutely. It's just like another tool in our toolbox when we're designing software. Talking of data types, this one's caught me out a few times where a type definition isn't equivalent to its raw primitive data type. a type-defined enum isn't the same as an enum. And so in your type specialization structure, if you want a case to work with all enums, but you wire in an enum type def, that case won't compile. To get around that, if I want something to work with all enums, type defined or otherwise, I will use a format into string function. And that function will work for strings, booleans, enums, type defined or not. But yeah, if you strictly type an enum, that's not going to work for type defs. Okay. Or vice versa.
And that's it for this presentation. So I hope you all liked it. We made it. I hope you all liked it. These were some of the lessons learned. So thank you also, Tom, very, very much for assisting, coming in for this presentation. It's been such a help, and it is a nice change of pace. So thank you very much, Tom.
Oh, thank you for having me.
Okay. If you have any questions, feel free to ask them to Tom and me. If you have anything specifically related to G²CPU, on how to use it, whatever, feel free to contact me on info@g2cpu.com, or if you just want to know more, just go to g2cpu.com.
Yeah. And yeah, throughout the GLA Summit, feel free to reach out to either of us, have a direct chat, or you can contact me on LinkedIn if you want.
And also, for those of you that want to use GPU computing, I have another presentation tomorrow discussing how to use the new features in version 1.3 on how to use multiple devices at the same time with frameworks like DQMH and Active Framework. So definitely something to look forward to.
That's going to be super neat. Looking forward to that.
Yeah.